first. Now recording start, and then let's turn on Tencent. Okay, anyway, homework. Let's see. So the homework. Open Tencent. What's going on? My computer is not working very well. Sorry. Dropbox. So scalar QED I want to talk about, and then so to let's write down Lagrange. Okay, scalar homework. 5. Last problem, scalar QED. So Lagrange is given by minus a quarter plus d5 and d5 star. I think that's the case. Let's see. Okay, so somehow Tencent is also working. Let's check more precisely what was the problem. Sorry, I'm disorganized today. What's going on? Okay. Good. Minus m squared. Okay, so that's a scalar QED, and we need to decompose this. Why? Sorry, I don't know why Tencent is keep mentioning it. It's not working. Anyway, students is supposed to come. I don't need to connect to Tencent. But anyway, I hope it's okay, Tencent. Actually, one student's already come to Tencent, so but it's work. Okay. Anyway, so this is a scalar QED where the mu is given by. Sorry about this morning. I'm already disorganized. So this is the case. Here it's just same as before, same as what I tell you. And we can decompose this one is equal to phi mu plus I e mu, and phi times phi mu plus minus I e mu phi star. So therefore, this is equal to this part can be decomposed like a phi mu, del mu phi star. And then plus I e mu phi minus phi star. Okay, and then what we have is that the plus I e square and mu. Oh my goodness, sorry. I think I should put the mu upwards. Mu up, sorry. Mu. Then I have to be careful about a bit. Oh, what I'm doing. Sorry. I'm so sorry. There must be derivative. Do you agree? Do you agree so far? If you don't agree, just tell me. And the mu. Mu phi. Do you agree with that? Then maybe this is minus sign. Do you agree with that? No? No. Okay, where?
There is a phi in the second.
There is a phi in the second. Okay, good. Okay. Thank you very much. So one should be Okay, phi star. Okay. I'm very sorry. Okay, acts on the phi star, and the next is minus phi mu phi star minus I e square and mu phi. Do you agree with that? Is it okay? Do you agree? Okay, good. So this is the case, and then so if you add the master, so this will give you just a free scalar, complex scalar, this, and this will give you interaction term. This will give you interaction term. And one has to assign the final rule for this one, and then this is the okay. So final rule for this one. So for scalar theory, so there's a line like this way. So this way it will give you I over p squared minus m squared. You have to be careful that there's a direction, because here you have the particle and antiparticle. So as you did in the homework, you have both creation operator A and B, dagger and dagger, for complex case. So if you recall, like a first or second homework, I already forgot which one it is. You have a two creation operator. One is the particle, scalar particle, and the anti-scalar particle, or complex scalar field. So therefore, you have to really need to write down the direction. Okay? If it is outgoing, it's a particle. If we incoming, it's a anti-particle and so on. Anyway, it depends on final initial state. And here, what we have is something like this one. Mu. This is I e p mu. I think this is what are the sign of this one? P mu minus and plus p prime mu. Okay. So this is the case. Yep. So since so here you act on the the usual particle creation operator, and this anti-particle creation operator, which has an opposite to Fourier expansion. So one is the e to the, for instance, minus ipx. The other is minus plus ipx for this one. So therefore the sign cancel, and that will give you this one. And then that is coming from here. So one can give you p mu and p prime mu, because anti-particle. And here, so what we have is something like a like this way, and then mu and nu, and this is equal to 2 times I e squared g mu nu. Okay, I think this is it. I think it should be okay. I think over here, so as you can easily see, this can be written as the I e square, right? Wait a minute. So mu, nu, and g mu nu. So this is the case. So, and unfortunately, I don't know why, but here it should be just I times e squared. I don't remember why. Why? The E square is really coming from here, and the mu is mu and nu. So this is the photon propagator or whatever photon vortex, and this is phi and phi star, and this is mu and nu. And the coefficient, so the factor of 2 is symmetry factor, just swapping n. Okay? 2 is the swapping of the and then let's see. I just don't remember. So okay. This I really coming from the expansion of the Dyson series. This I really come from Dyson series. Now I remember. So this I coming from Dyson series. So recall that you have to expand it e to the I time ordered I times h. Sorry, I think the time order e to the I from hi dt like this. Minus is it minus or plus? Can you check my lecture notes? Minus, right? Is it minus or plus? Minus, right? Okay, so this is Lagrangian. So if you go to Hamiltonian, you get a minus sign, and then that minus sign cancels this minus sign, and I remain. Okay. Are you guys following? Is it okay? So this is the final rule for scalar QE. Okay. So given a Lagrangian, one can read off the final rule. And next is the question is the last problem. What was the question? They just find the find a correction to this vertex. Find a quantum correction to this vertex. Okay. So this leading order is this guy, but so most of people, as I explained, this is mu and e and e prime. Most of people apply this vertex to here and like this way, and then did the same thing as before. This is one diagram. One can cook up for one loop, other one loop. But this computation is almost similar to the what I explained in the lecture. On the other hand, so here, so this is the scalar QED has the extra property. So the usual QED, when you say QED, it's electron is fermionic. But here it's a scalar particle, and that will give you another vortex. So therefore, one can just cook up the another. So one loop, there's a contribution, something like this one. So here, you can take this kind of loop. So here, at this point, you can apply this rule. We have this vertex have a 2 photon line, and then 2 scalar line. That is exactly this one. Okay. So therefore, at the one loop, also this diagram should contribute. Do you understand what I mean? So therefore, this is the P and the P prime and the Q, and then whatever, maybe K. I call it K, P minus K, something like this one. And then, as you can now you notice that there is one more diagram. So this is very important point of this problem. In fact, I wanted to notice you guys, and then of course one can do the same thing in here like this way. Okay. And then this I call it the P and the Q, and here you have a let's see. I call it this my P prime, and I call it K prime, and this is P minus P prime as K prime, and that's fair to say. So these 3 diagrams should contribute, and then maybe Okay. And it's very, very, very simple exercise to do this kind of computation. Okay. Let's see. So the first diagram is very simple. Okay, let's. Okay, it's a very good problem. So let me do it for you a little bit. So I didn't print out this part. The first diagram. So let's call this a 1, and then maybe I call it. Am I calling this 2? Yeah, this is called 2, and this is called 3. So therefore, one has to. One is something like a D. I mean, you just start it. I mean, okay, and then k squared minus I. How do you call it? Okay, let's follow my. Yeah. Okay, I call this one sigma mu nu. Okay, so I call in this point is sigma and sigma and rho. I think is that what I call? No, nu. Sorry, sigma and nu. And then it's super simple to do that. You have to apply the final rule here. So you have a P and a K, right? P, K, so therefore you have to apply this one, which means that the minus I, and then P mu plus K mu, and then you put the propagator minus I, G, nu mu, and then you apply here minus I, E, times, so here, so K and K prime, right? K, oh, sorry, it's not mu, so sigma, sorry. Sigma, and the mu, and then K prime mu. And then, what was the propagator? K prime square minus I, G mu, what I call rho. And then we have the K. Is it okay? Okay, yeah. Minus I E. What's the minus E and the K prime rho plus P prime rho. So this is the diagram, the contribution. I hope it's okay. And oh my goodness, and I forgot to include this one. So I need to include this one. Yeah. And then, okay, it's a scalar, sorry, minus n squared. Sorry, minus n squared. So this is the scalar propagator. You have to include minus. Oh my goodness, so the. Sorry. I'm very sorry. So this is just a scalar propagator, and then what's important is the here. It's a photo propagator. I made a mistake. Sorry about it. Minus what was the momentum? P minus K square minus IG rho sigma rho. Okay, so this should be the answer. Yeah, this should be the answer. I already omitted plus I epsilon. And then what you can write down is the, so now if you just play this diagram, so one can just write down d4k. Are you guys following what I'm doing? Is it okay? I made a lot of mistakes, but this should be scalar propagator here, and this scalar propagator this one. And then I call K prime as the P prime minus P plus K square minus N square, and then P minus K square And if you just manipulate this you can just write down this is minus p prime minus p plus k mu, and in the front you something like this one, and then you have a product of p plus k not k p minus k 2p prime plus p minus k. So this is what you get from first diagram. Okay. And second, okay, I have to be careful. So d4k to 5 to the fourth. Okay, let's do the here you have the what did I go? This is sigma I call it. Okay, I call a sigma here and mu here, right? I think this should be okay. So then what we have is that the minus I E P, so this is same. So this is same here, but you just apply this curve minus n squared I is the same. But here you have to apply this diagram. This diagram. So I think this should be mu. I mean, I call it like a mu here. So therefore, so this diagram you have to apply this diagram. So therefore 2IE squared G sigma mu. Is it okay? Sigma mu. And then sigma mu oh, I see. I think you have to be a bit careful. Okay, so I call it mu and nu. So I think it's sigma mu. And then you have to include the photon propagator nu sigma, and then p minus k. Do you agree? Is it okay? Is it okay? So here, strictly speaking, you have to decompose this red one is this part, and then you have to apply propagator here. Okay, and then you use blue one here. So this is blue. This is the red and the orange. Red and orange. So that's the case. And you do the same thing for, and if you manipulate this one can just write down is that this is equal to 2EQ D4K. Okay, let's go. And then, this is super simple, P plus K. So the number 3 is also simple. Number 3 is the same thing. So number 3 is you have to swap the role of the K and P prime. I think let me write down the answer for you. Yeah. So the role of the swap role on P prime and the K prime. So which means that the 2EQ K 2 P plus K prime and K prime minus M squared, and then P minus K prime, I think. Is it correct? Seems like not. Why is that? So this I call it K prime. So I call it K prime. Okay. Just a moment. K is equal to, of course, this is P prime minus P minus K can be written down like this way. So then, sorry, just a moment. I need to do the change of variable to get what I have written in the. Oh yeah. This is P prime. Sorry. Yeah. Good. And then plug. If I write down the K prime as a P prime minus P minus K, then this will become the mu, right? So this will. I hope I don't make a mistake. Am I doing mistake? Let me think, just a moment. P, I think what I did is here. P plus. I hope I don't make any mistake in the. Yeah, it looks okay. So then to EQ. P prime minus P plus K square and square. And then P prime minus K prime is what? K prime is the P minus K square. Do you agree? And then here is something like this should be P prime, sorry, P prime, and then this is 2P prime minus P plus K. Okay, good. This is exactly what I have written. Good. Do you understand what I mean? So I just, from here to here, I just put the K prime goes to this number. And in quantum field theory, it's a very important thing is that it's not so important to evaluate each diagram individually. Because I mean, in quantum mechanics, you cannot really tell that the contribution, you cannot separate contribution from here and here separately. So therefore, first you have to do is that you have to sum over 1 plus 2 plus 3. The reason why I make this kind of change is that if you look at denominator, so you have a common denominator, right? Common factor in denominator from here to here. To move from here to here, you just want to have the common denominator from upstairs. So therefore, it's easy to sum them up. So if you sum them up, what you get is EQ d4k 2 pi to the fourth. And what we have is the denominator something like k square minus m square p prime minus p plus k square minus m square. Okay, and then p minus k square, and then n mu. So n mu you have to really compute. You really need to compute if you sum them up. Okay, sum them up. Then apply Feynman rule. Feynman parameter, just introduce Feynman parameter and do the weak rotation and power pillars, and then obtain the number. Okay, so that's what you're supposed to do. And then unfortunately, not so many people have noticed these 3 diagrams. So therefore, I give you 1 more week to solve this problem. So I derive at this point. So what you need to do is compute n. Seriously, they just add them up. and apply the final parameters, and then do the weak rotation and power balance regularization, and obtain them. That's what you need to do. So I will give you 1 more week to submit this homework. So next Wednesday. So whatever method you can do that. I mean, you can submit like whatever, a PDF attachment or just next class is also okay. So I just give you the 1 more week to solve this problem. Okay, so that's one point I wanted to make. So yeah, I thought it's a bit. So it's a very good exercise that you can just not you have to really need to think what the Lagrangian. You need to read off the final rule from Lagrangian, and then from final rule, what is the all possible diagram one can consider? So for quantum correction, that's a very good exercise to do. That's why I just give this problem. Okay, so that's the case. Any question at this moment? Okay. So that's the scalar QED, and the scalar QED show up in the this diagram. I forgot this diagram. One PI. Oh yeah. And also this diagram. 1 PI. So I mean, yeah. So as you can easily see, I mean, anyway. Yeah, I mean, should I tell you or not? I mean, anyway, so you have to consider all possible one-loop diagram which contributes to this propagating homework 6. So it's not necessarily one diagram which contributes. I mean, naive guess is that anyway. If I give this hint, you can easily find the diagram. So I think it's actually. Okay. Any question this moment? I mean, for instance, okay, I will give you some hint. So I mean, naive diagram is that the last time. So this is naive diagram. So, but of course, you can just consider if you use this diagram, one can hook up this diagram. Right? So you have 2 diagrams that contribute to scalar QED. Do you understand what I meant? So that what you need to do, you really need to sum them up. Okay. And then when you sum them up, you have to, like computing each diagram not so important. You have to first sum and evaluate, like this way. So computing each diagram doesn't make so much sense, because we cannot distinguish in the experiment, okay? So we cannot see what's going on inside. That's why we call it 1 PI, right? So what we're interested in only order of the coupling constant. So therefore, first you sum them up and apply this final parameter, and that's the meaning of this homework indeed. I mean, of course, I mean, don't be afraid of so much complication of calculation. I mean, of course, doing calculations tedious, takes a lot of time, but the important thing is to understand what it means. Okay, so what it means. So therefore, of course, a human being will make a lot of mistakes, but mistake in calculation is not that important. But the important thing is to understand what's going on. So here you have to really understand what's going on in quantum mechanics in one loop, given a Lagrangian. So yeah. Anyway, so that's the meaning of homework of this scalar QED. So you have to be careful. Okay, so let's go back to the lecture. So I decided to swap the order of the teaching because the the normalization. First, I decided to do all the computation of VI, and then after that, so what's left is we compute Z1 and Z2, and magically last time, so we just showed that Z1 is equal to Z2, and what's left is Z3. So by explicit okay, I think maybe I should write down here. So by explicit calculation, we show Z1 is equal to Z2 magically. Z1 is coming from this diagram, and Z2 coming from this diagram. This diagram. And then, so that's what we did magically. So it's a super like a magical, but I'm going to show this is a consequence of Ward-Takahashi identity. This is the one of the highlight of this course. Ward-Takahashi identity. We guarantee this one. So I'm going to show, but before then, okay. And also, what we have done is that so electron mass is indeed depends on the scale. So m physical is equal to m0. Yeah, m0 times 1 plus 3 alpha for phi log lambda square m0 square plus order alpha square. So that's what we have shown during this computation. So when we do this kind of computation, we just saw that the propagator of the classical propagator is shifted like this way, minus sigma 2p slash divided by I, and the position of pole will change from m0 to m physics. By evaluating the sigma 2, we just show the one correction to the mass of electron. And this means that so m0 is called bare mass. The mass of electron at the energy scale lambda can be understood. And m physics is the scale we measure it, and then we know that this is around the 511 keV. Okay, 511 keV. Therefore, to get this mass, so since this quantity is very big, very big, m0 needs to be very small. That's what we have learned. M0. So therefore, if you go to the high energy, the mass, bare electron mass is very tiny. So which means that the most of the electron mass is coming from this quantum correction. On the other hand, without quantum correction, the bare mass, the naked electron is very skinny, really tiny, has a tiny mass. That's very like a quantum phenomenon. So the mass of electron really depends on energy scale. Okay. So that is the new quantum phenomenon we learned from this calculation. So the mass of electron really depends on the energy scale you measure. So our ordinary scale, the mass of electron is this amount, but if you go to really high energy, it's almost massless. That's what it means. So that's another lesson we learned. And then, so the from coming lecture, what we first, I mean, which one do you prefer? I mean, I can show first this one and go to Z3. That's also okay. But I think considering the homework, I think it's better to first homework 6. I think it's better to first show this Z3. Then you can just immediately apply this what we learned today to the homework 6. The last problem, homework 6. So the plan is to first do the Z3, first computation of Z3 for computing this one. Computing this one for one loop correction to Z3 first. And then next word Takasha. And that's the plan. And as you can see, I'm going to erase the blackboard here, but before then, so we are going to compute this diagram. It's similar to, this is the electron propagator, this is photon propagator, one root correction photon propagator. I just give you an answer that the, so scalar propagator, as you can easily see, the corresponding diagram is like this way, right? But of course, there's another contribution to here. That already noticed the people here is, this is also allowed. Okay? This is also allowed for scalar. So the reason why I picked the QED, usual QED, electron is the fermionic. QED is that the, I mean, scalar QED, you have to sum over two diagrams, so it's a bit more complicated. But I mean, anyway, so that's why I just chose the. Yeah, I mean, if you submit this exercise, I mean, I just give you just honor score. I just add the score to the one you did in the previously. So anyway, seems like most of people didn't have a time. That's my impression according to from my observation. So so I will give you one more week so that if you want to do the calculation, it's yeah, you can submit next week. Bye. Okay, so we will do the same exercise to do. Tired. So let's call this one. It's so 1pi is I sigma mu q squared. Okay. And the Fourier quantum. So I think exactly we would repeat the same analysis before evaluating this one. So we will do the same exercise what we did for this one. And from, okay, so evaluate this one. So here, the mass depends on energy scale. Then from now, what we are going to do is the E, electric charge, which appear as a coupling constant, I, E, mu, psi, gamma mu, psi. So this term will appear as a intuitive interaction term, right? Interaction term. So you already learned. So that will give you this vertex. This vertex. It is interaction term. So therefore, electric charge can be understood as a coupling constant in QED. And this coupling constant, by evaluating this diagram, we will learn even coupling constant depends on the energy. That's very, very important concept. So the coupling constant, so that just give you, before going to the detail, before you lose the big picture, so let's talk about big picture. So by evaluating this one, okay, so let's move on. So how this affects the coupling constant is as follows. So now of course, what we learned, the fully quantum collected this one is of course this one plus this one, 1pi, plus the same thing, 1pi, 1pi, and dot dot dot. So now for this is equal to, we already learned this, minus I g mu nu q squared, and then we do the same exercise. Minus I q squared, and then plus sigma, I times sigma goes nu minus I q squared and dot dot. Okay, and then so that's what is going to happen. And then I will show you this one here. So the word Takahashi identity again tells you that the q dot p, q dot pi, which means q mu. So this is word identity is equal to 0. This should be the case. And here, as we know, so the exchange of mu and nu, it should be symmetric. Photon propagator exchange. So therefore, this g pi mu nu should be written in the g mu nu is as the ordinary photon propagator, or it should be proportional q mu and q nu. Then it's symmetric under the exchange of mu and nu. Okay. Okay. Mu and nu, if you exchange mu and nu, so both are symmetric. And then, so this is word identity. We were going to word identity. So if you assume this word identity, I'm going to show this one in the maybe next lecture or at the end of this lecture. I don't think I'm not sure if I have time. Most likely no. But it's better not to rush. Q squared g mu nu minus q mu. So you can just write down like this one. So if you contract with q mu, as you can easily see, if you contract with q mu, this will give you q squared q mu. If you contract q mu, okay, q mu, then this will give you minus q squared q nu, which is equal to 0, right? Do you understand? Do you understand? So therefore, if you assume this word identity, and pi mu nu is symmetric on the exchange of mu and nu, the Lorentz symmetry will tell you that this should be written in terms of g mu nu and the q mu q nu. Therefore, this is the only combination what you get. And so if you're already start solving a homework, if you solve this problem, if you evaluate this loop integral, that also should be proportional to this quantity. That's why I asked in the homework, that at the end of the homework, if you evaluate this one, the loop diagram should be equal to proportional to this two. Because of word identity. Okay, so then if you assume this pi mu nu takes this form, then you just plug that one into here. So this is equal to minus I g mu nu I don't know why I have written like this one. Sorry, I think that's a very stupid way to write down. Election mode is very stupid. It's very simple. So we already know that the pi mu nu is equal to is proportional to this one. This pi is really this guy. There's no index in mu nu. So Lorentz invariance and then this word Takashi identity will tell us the pi mu nu is proportional to this one. And plug that into here, you get the first term, and do the same exercise here. But should I show you? Let's do that. Simple exercise. I mean, anyway, this is the most important part of QFT1. And most of the courses do not reach this part. So most of QFT1 do not reach this part, unfortunately. So Q square G mu sigma minus Q mu Q sigma and Q square G sigma nu minus Q. I'm sorry. I hope you can understand my Q and you can distinguish the Q and G. Sigma Q nu. So my handwriting is horrible. This is G and this is G. Okay. And do the Lorentz contraction. What we have is the from first term Q square delta G mu nu. G mu nu. And if you apply this one, you have a Q square times here you have a Q mu and Q nu. And this multiplication will give you the same term. So this is 2. That's fine. And if you do the contraction with this one, it should give you the Q square, because this Q sigma will get Q square, and what's left is Q mu and a Q nu. Sorry. My handwriting. Sorry. Q nu. Therefore, this is equal to Q square G mu minus Q mu and Q nu. Do you agree? Is it okay? So you can just factor out the same term here, and then you have Q squared. Is it okay? And this Q scale will cancel with this denominator in here, one of the denominator here. Okay. And what's left is this guy. Do you agree with that? Are you guys following? Do you want me to repeat my calculation? Hopefully, okay. Hopefully you understand it. So this middle term is just crossing term. And the first time is just this times this, and the last time this times this, and magically the crossing term and the last term cancel up to factor. Okay. And then you get the common factor here. Okay. So that's why you can have this one, and then you can just, I'm going to erase this one, and this one is equal to, you can further simplify it. Minus I Q mu Q nu Q square plus minus I Q square 1 I. Do you agree with that? Are you guys following? So let's see. This can be written as the 1. Okay. So this one, just put this one into, incorporate this one into here. And then you just add 1 plus. Then the difference is this term, right? So therefore you have to subtract. So which means that the minus I q mu q square and square. Okay, do you agree? Okay, and this one is just a geometric series of 1 over. Right? So that's why you just summarize 1 over 1 minus pi. Okay. Okay, so it's a super simple. Even though fully quantum corrected propagator, what we need to do is just evaluate this pi. Before we evaluate pi, what we need to do is they applied the order identity or not. I mean here this is a propagator, and in fact what's relevant is only this term. In fact, this is only relevant. And the other term is if you contract with the fermions, they will vanish. Do you understand what I mean? So let me give you the example. This is also another. It can be understood another consequence of word identity, but I can give you some explicit example. Of why this has to be managed once you incorporate in the contract with fermion. So what's relevant this term and the other term proportional q mu or q nu are not relevant because so for instance, if you contract with like a fermion, so the diagram we are interested in, for instance, you can consider this kind of diagram. And here we know that this is proportional to minus I q mu q square plus minus I q square 1 over I q square, and then g mu nu minus q mu q nu q square. And then so this is a propagator in this part, and then what we need to do is a contract with vertex here, which is the so let's call this maybe p prime and p, and you already did, right, many times, k prime and p. So then here just something like up, and then what was that? U bar. Gamma nu UK. Okay, so that's this diagram, and we know we just applied. We know this is this is Q, which is equal to P minus P prime minus P, and which is equal to maybe K minus K prime. Okay, do you agree? By moment of conservation. So therefore, if you take the slash of Q and gamma mu, if you only look at this one, so you just concentrate this mu part and this part, that will give you U bar P prime Q slash UP. Okay? UP. And we know that this one is equal to U P prime P slash prime and P slash and U of P. Okay, do you agree? And if you use, so this is plane wave equation solution, U bar and U is a plane wave equation. This just give you M and minus M, and this is equal to 0. Okay, do you understand what I meant? The P slash prime acts on this one will give you M, because it's just equation motion. P slash acts on U, it will give you M. That will count them. So that's all the term. So this propagator so this is, I call it fully quantum corrected propagator. Once you contract with the external parameter, which is the fate of this this propagator, the proportional Q term is irrelevant because that will give you just zero. So what's relevant is G mu nu part. Okay? So therefore, effectively, what we have is that I'm going to erase. Is it okay to use it? Maybe I should bring it. So effectively what we have is that effectively this means that this one I don't know which direction I take Q square, but that is not so irrelevant. So it can be written as the 1 minus okay, so one can just write down like this. Do you understand? Is it okay? So I just pick only this term and just throw away the other two terms, which is proportional Q mu and Q nu. I just pick only this term, and that is this guy. So therefore, so as I mentioned, so this can be written as a Z3 minus I G mu nu Q squared. Q squared. So therefore, this means that the Z3 is equal to 1 minus delta Q squared. Sorry. When you say Z3, so this should be put in 0. Q squared equals to 0. So that's can be understood as this one. Okay, so that our goal is to compute Z3. So what we need to do is this evaluate this pi. So which means evaluate this pi. And then before then, why it has to do with the running coupling constant. And I already told you that the QFT will be taught by Xiaoling Yu. And I think in QFT2 you will learn so-called beta function, which is the also beta function, but I can just introduce beta function now briefly, and then in QFT2 you continue to learn beta function a lot. So here, as I have written like this way, so this diagram with the proportional E square, because I mean vertex will give you E, this vertex will give E, and then G mu nu Q square. And if you fully quantum corrected diagram is that one I have written there. Is proportional to E square Q square, no, G mu nu, sorry, G mu nu divided by Q square. 1 minus delta Z. More precisely, this is Q square. I think I should write down like this: Q square and 1 minus Q square. And again, this guy has an infinity, and as I mentioned many times, and as last time the audio was not good, but as Beta mentioned, what we are interested in the difference. So you have to renormalize to get rid of unnecessary infinity. Well, you have to take a difference, okay, from this guy, this propagator, to this propagator. So what we are really interested in the difference, I call it this pi renormalized. So usually I'm sorry, I think the difference means is that the sign should be opposite. Sorry, the sign should be opposite. So this one, this quantity is equal to, okay, a pi renormalized of q squared. Sorry, I think this quantity is equal to 1 minus pi renormalized. So if you take a difference between q squared and the 0, right, one can have the meaningful dependence on energy level q squared. So now, effectively what we have is electric coupling constant here. So this is effectively E renormalized, I think, or effective, I call it. Effective is equal to E squared minus 1 minus which is equal to E, I call it E0. Oh yeah. E squared 1 minus delta Q squared plus. So this is what we have. This is what we have. So, so the effective electron coupling constant at the energy level minus q squared, really you need to compute pi. Really depends on energy. And some people just mentioned it. I mean, q squared is space-like, as you already noticed. Some students ask me why q squared q is space-like. I mean, as I mentioned, so this is the whatever q, and this is I call p and p prime, right? Okay, and p and p prime is the some people. I mean, so this is time, and this is space, and this is light cone. Light cone, this is space. Light cone, and this solid line, solid straight line is electron. So therefore, it should satisfy the coefficient motion, which means like this way, right? It should be, if you consider E and P. So E and P, so they, you understand, right? P and P prime should be the vector like this way. The P and P prime is something like this, is maybe P, and this is P prime is like this way, right? Do you understand what I mean? And of course, if you take a difference, Q is P prime minus P, which means this one, right? This one, right? So therefore, it always becomes space-like. So therefore, if you take a Q squared, it should be negative in the in this convention. G mu nu is equal to 1 minus 1 minus 1 minus 1. So therefore, it's a space. If it is space-like, it's a negative, right? So therefore, you have to include the ordinary energy level. You have to include minus. Do you understand what I mean? Some people always ask me. Some people, I already forgot the last time or 2 lectures ago, why this is space-like. This is the reason. Is that okay? I hope you understand. But anyway, so electrical coupling constant really depends on energy scale Q squared. And as we will see, so this is energy level. Energy level is equal to minus, what I'm doing is, energy level which is minus Q squared, and the electrical coupling constant E effective, minus Q squared. And the low energy, I don't like this one. I think I call it alpha. Alpha. Okay, now I remember the formula for alpha. Oh my. So, and the effective minus Q squared, and then alpha minus Q squared. Effective fine structure constant depends on energy. And of course here E, you have to set which scale you. So this one, the reason why I take a difference is that this E effective Q squared equals to 0 should be E squared. Do you understand what I mean? So if you set q squared to 0, they cancel, right? They cancel, and you get only E. So therefore, here E is really E q squared equals to 0. And E q squared equals to 0. So what we are doing is that the first set, the alpha is we know at the energy scale 0 is 1/137. That we know. Our really low energy, our energy scale is very low. You start with the 1/137 fine structure constant, and then it depends on the energy. Depends on the energy either this way or this way. And in fact, actually, if you go to the high energy, the electrical coupling constant grows. Grows. And then, in fact, the low energy is very small, but as we will do the computation after the break, it starts growing. Okay, the electric coupling constant growing as the energy scale grows. Then eventually this perturbation theory breaks down. So that the high energy you need something more like a well-defined quantum field theory, which is the so-called Weinberg's Salam, whatever, glacial electroweak theory. So you have to combine electromagnetic theory and weak theory to make the well-defined theory at the high energy. I was planning to give a lecture in QFT2, but unfortunately, development forbids me to do it. But anyway, so after this computation of this diagram, I already didn't erase. So after computation of this diagram and we compute pi, we will see that the coupling constant grows as the energy scale increases. Okay? And then if the coupling constant grows, we did the perturbation expansion in Dyson series. Right? Dyson series is essentially 1 minus I coupling constant hi dt plus minus I e squared hi d squared d whatever dt1 dt2 and dot 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 dot. So we did a perturbative expansion, and usually we only evaluate only first one. But we assume this E is very small if you do the Dyson series like this way. But if you go to high energy, this breaks down. Okay, this perturbation, because each time it becomes bigger and bigger as you did in homework. Okay. In the homework, in this quantum mechanics. So therefore, we can no longer use this quantum Dyson series for high energy. So then you really need a new theory to make the quantum theory make sense at the high energy. That is Weinberg electroweak theory. That's the content of QFT2, and I think it's a good time to take a break, I think. And then after the break, I will play one video, and after that, I will evaluate this back. Let's take a break.
Because there's C in so that it will so this is this plus this, and there's yes here, and so
If you do the computation, look here.
I think that there's also a one
Yeah.
C here, and these two terms will
We count them. Okay, thank you very much. I mean, I mean, I mean, here. Because I mean, the equation motion for photon is q squared equal to 0, right? The classical level. Yeah, it's an object case. That's
So we should use the equation of motion to add the Q square.
No. Here, we look at the pole. Pole of this propagator. So as you recall, so when you do the this diagram, then what we have is that the I over p, right? No, this is okay. And then this and 0. This we write as 2 I p slash minus m, right? D2 is really the residue of this pole. So therefore, here what we have is that we did is this is equal to I divided by slash minus m. 1 minus partial sigma slash, and then this is p slash is equal to m. Right? And this D2 is equal to D2 is the 1 minus P slash inverse, right? That's what we did. That's what we did. So therefore, this is residue, really residue of this property. So therefore, we have to take a residue of this property, which is really the Q squared. So the residue does not change in this process. So this doesn't have a other pole. So therefore, D3 should be residue. That's why you have to put the Q squared.
That our final exam is closed book or open book? Or
Open. The final example, open book.
So I can bring my text.
Yeah, textbook, and you can also bring a laptop if you don't connect the Wi-Fi.
Oh, thank you.
And then, oh yeah, then video, play video. Sorry, before then, let me go to restroom.
就是一眼看不出来是多少。对，哎对，对啊。然后他的意思大概就是那个那个派，那个什么情况能够测到？不知道，那什么时候会测到跟它不一样的质量？那个高等标准质量的问题。
然后这个问题就在于我们做积分的时候，我们说进去的话，
那个答案呢？
就关键就是在于，我觉得是我们做积分的时候，我们就读上个积分，然后用一个进程，然后得出来就是阿尔法等于1除以1加等于1加4，然后但实际上你真的积分是
做什么积分？代数系数。
我，oops。
发散积分就是通过奇迹为什么会发散？还是这个逻辑。
And hopefully what's going on? How can I turn on the E? Sorry, can you help me? Hmm? No, I don't understand this modern technology. Can you help me? Oh, back over there? How can I? Oh. Hmm? What's going on here? How can I turn off the switch? I don't know how to do this. Why is it so? Oh yeah, it works. I don't know why. Anyway. Okay. Okay, maybe I will play like a 2 or 3 video. Unfortunately. Okay, maybe one video is enough. I don't know. Let's see. And what I should do is just connect this one to here. Yeah, I don't like this kind of high-tech stuff. It's too high-tech for me. And then connect this one too. Okay, let's try.
And he talked about physics, of course, a great deal. And there I argued with him a lot because
Still audio is not that good. Oh, maybe. Okay. And then wonderful. Why? Ah. What's going on? Hmm? Yeah, that one maybe. Wonderful. Thank you so much. And then, why is it so? Okay. It's a bit different from last time. What? What's going on? Okay. But I just want to give you some script to you first. Translate. Okay, this is translate. And then I hate. Okay, I sent you transcript. And this is. I hate this. Hopefully it'll work. So this is about talking about Simon. This is he's Freeman Dyson, and then unfortunately my device is not that good. And then I don't know how to connect it. One person currently brought it to me, but unfortunately it doesn't work. But anyway, let's try. It's a bit better than last time. Slightly better. So I just send a copy, right? And then I think this is talking physics with Feynman, and this is path integral. This is the theme of this video. And he's going to talk about the Feynman diagram next. Okay, let me give you transcript again. It's kind of annoying, but unfortunately I have to. Okay, the Feynman diagram next. they had a fun talking. Okay, let's move on a little bit, and then I just want to linking ideas, Simon. That I really wanted to play. This part was really fun. Let's see. It's a bit longer. I think script is longer. I'm so sorry. But, I hope I copy and paste everything to you. It's a longer one. Let me. This is combining idea of Feynman, Schwinger, Tomonaga. So this is really what he does in like this Dyson series. This is the work of Dyson series. So according to this Dyson, the time ordering is essential. So they didn't understand the time ordering at that time, but the Dyson incorporated time ordering to make everything work together. Okay, I can send you a link of this one. If you're interested, you can have better audio later. And then let's stop. Yeah, it's a very interesting interview. Even though both Beta and Dyson have passed away, but we can still listen to their voice. That's quite amazing. Okay. So 45 minutes of what? To the conference. And so we are going to compute this guy by dimensional regularization. I'm still recording, right? And don't forget that I couldn't use the speaker. Please pick up before you leave. I forgot to. Yeah. Okay, let's do the computation. Where should I erase? There. So some people ask me about final exam. Final exam is supposed to be the 开准. And you can bring whatever you want actually. And then some people ask me if it's very difficult or not. I don't know. It depends. It's easier than of course the usual homework. I already forgot I already created the final exam. Essentially, what you need to do is apply final rule to diagram and then compute. But I'll let you know the more detail about final exam in coming weeks, not now. Okay, so let's do this computation of this one on the diagram. So for first order alpha, I call this is pi to q squared. So the goal is to compute pi to q squared. I call it pi to q squared. And then since this is still a roof, if you have a roof, you always have minus sign. As I mentioned, so you always have trace of side up side. And then when you contract with together, you have to always have a minus sign. Because I mean, this sidebar needs to bring 3 times, right? So therefore, we have a minus sign. And then the OK divides in 4. And then trace. I need to finish this calculation today. I can get there. Okay, so this is what we want to do, the computation. So this is the calculator here. So, and you already get familiar with that. I hope this calculator will give you this guy, and then yellow part will give you this guy, and then these vertex will give you this part and this part. Okay. Okay. I hope I understand. So we would like to evaluate this one we can also evaluate this one the power dealers, but this time we will use so-called dimensional regularization. Dimensional regularization was essentially introduced to Boltzmann as proved in Amsterdam, in Netherlands. In 70s. It's a much more elegant way to do this kind of like a regularization than Paul Billers. So I think QFT2, I don't know how he teaches, but the QFT2 you have to use dimensional regulation often, I guess. But you never know. Okay. But before going to DIMREG, people use DIMREG. We are going that will again use the final parameter to do the computation. So again, we apply final parameter. This is you have to get used to it when you do the quantum theory. Unfortunately, you don't want to take. Why? And final parameter. Again, I will keep some part. Okay, so x, y are final parameters, and they just take a linear combination of 2 denominators, and then you have to do this first. And then you just manipulate a little bit. And this is equal to one x over and I call this one is L. I call this one L. And this one is equal to delta. I think minus delta, I think. Yeah, minus delta. Well, the difference is just sorry, L squared. L squared. And we have to deal with the numerator. Numerator is an unknown part forward. 50. Then I should erase which part. And numerator is a long part. So numerator is the trace of gamma mu is flash of m gamma mu. So it's very nice that the dipole time, so they just use a gradient to move from Berkeley to Princeton for a week. It's amazing. And they teach it on the class. That's very good all days. And then we have to apply this one again. Trace of sigma is equal to G minus G. I'm not going to write everything. You have to fill out the details. Times 4, right? As far as I remember. Is it correct? And then trace of gamma mu is equal to G mu times what? Again 4? Again 4. I'm not going to fill out the detail of the indices. You should just take a look at it. We just need to apply for this one. And then what we have is that the for K mu K plus Q plus 4 K mu K plus Q mu minus 4 G mu times K of K plus Q minus M squared. Plus what we have. And then you need to change a variable. So I call it, so we need to change a variable to L. So L and so this one is equal to, I mean, just need to do computation. Okay, let me give you, so just change it, so just use L is equal to this one and rewrite everything in terms of L. But for L mu minus 4 1 minus x x. I'm going to skip some parts because I mean it makes you a bit bored. I mean, you just need to do computation. It's more time and you can't complete it, unfortunately. I mean, you guys are physics students, so this kind of stuff, if you skip that one, it's the same as just reading like a science novel. So, but if you're a physics student, you have to do the calculation, and then plus linear in L. So in numerator, as I mentioned, so if the numerator is linear in L, it doesn't contribute in the integral. So do you recall? So you have to recall that the for L 2 pi to the fourth some m L minus delta squared, and the L is linear. This should be here. And as I mentioned many times last time, L squared minus delta m equal L 2 pi to the fourth is equal to 1 over 4 G mu L squared, and then L squared minus delta. This is what we did last time, but we need to slightly modify this formula from now on because of this dimensional relation. So there's some students ask me that why this is the 4. Because I mean, when you take the delta mu, so this is trace, and sum over mu, you get a 4. That's why, I mean, if you take a trace, means that when you take a trace, mu has to be lower. Okay, this index is lower, and you make it mu, right? And take a product, then you get the L squared. Okay, the same thing you have to do. Mu, just lower index in mu and turn it mu. And sum over mu, okay? That will give you 4. That cancels with 1 over 4. And then you get the same result, okay? Once you take construction. And as I mentioned, when mu and mu are different, they do not contribute because the same reason is here. The only contribution coming from mu is equal to nu. And Lorentz invariance will tell you that should be proportional to mu. That is fully symmetric. And then good symmetric, and also the Lorentz. So therefore it should be mu inside. Of course, in general, this is not true. If there is no integral, this is not equal to this. That you understand, right? This is only true after integral. If there is no integral, this is not true. Definitely not true. But because there's an integral, this is true. And then what is dimensional regularization? The idea of dimensional regularization is that so you start with D dimension, instead of 4 dimension, or 3+1, whichever you call it. Anyway, so we have to do weak rotation, but anyway, that is easy to perform. At the end of the day, so we would take and bring it to D equals 4. 4 minus 6. It's kind of 4 minus 6 to go to 4 dimensions. So the integral will somehow give you information about the infinity of this integral. Okay, so that's the dimensional regulation, the idea of dimensional regulation. So, this was the often used in the quantization of Yang theory. So when you compute I don't know. This dimensional regulation was introduced by Saltzman proof, and they show that using the dimensional regulation, the Yang theory is the quantum mechanically normalizable. So that's how they got the Nobel Prize. But anyway, I hope the Xiaoling Yu will tell you about that story. Okay, so then what we need to do is just apply. What am I doing here? Okay, so then apply this to dimensional relation to this integral, and then in fact this pi 2 mu of q square, q or q square can be written. So you just factor out 4 pi epsilon square. Therefore, dl 2 pi. Now no longer 4 here. No longer 4 here. I just replace with d dimension. And then L mu minus 2 1 minus x q mu minus g mu L square x 1 minus x square minus n square. That's the denominator, and times dx 0 1 1 over L square minus delta. So L and delta, yeah, delta depends on x, so therefore, oh my goodness, sorry. I think the way I have written is totally wrong sometimes, because then this depends on x, so I have to correct the direction dx. That's after ignoring the linear in L, and it's just massage this equation and you get this. Okay. And then now, so we replace 4 by d. So if you replace 4 by d, d and d, and this is b and d, then the trace becomes d dimension. D can be any number. Here it's not necessarily integer, in fact. It's not necessarily integer. So I just replace 1 over d. It's, I don't know, to be honest, I don't know why it works very well. Somehow it looks like a cheating, but somehow it works very well. D can be any number. It can be understood just real number. Therefore, if you want to encode an L nu, so you have to replace by this number. And once you do that, what we have is the one is the 3 minus d minus 1 g mu dl implies the d L square minus delta square. That is really coming from first term, really coming from this part is coming from this guy and this guy and this guy. And the rest of the term will be simplified to the following minus 2 1 minus x q mu and minus g mu, and I think this is just a delta. I think it should be delta. It's just it's not delta. It's delta. No, it's not delta. Okay. X 1 minus x q squared plus n squared. If I don't make a mistake in the notation, and then L d pi d, and then 1 over L squared minus delta. That's after manipulation. So far it's okay, and then do the weak rotation. If you do the weak rotation, what we need to do, I think we should use a different color. So what we need to do is that the DDL is I times DDLE, and also L square is equal to L square at times minus 1. Okay. That's what we need to replace it. So then I'm going to replace it as follows. Since you have so you just replace E here and E here and E here and plus sign here. So minus sign cancel with minus sign here, but here you have an I here. No, sorry. You have a minus sign here, but here is square, so therefore overall minus sign here. And then, so you have an I here, so therefore you have to be minus. And then we'll do the same exercise, but here it's super simple. You just have an E here, and E here, and plus. That's it. So now it becomes Euclidean. After weak rotation, this is weak rotation. And we need to do the integral. And I'm going to do it here. Okay. The original procedure is written in the lecture notes. I don't know how much I should explain it, to be honest. Okay, slightly I should explain small amount, minimum amount I will explain. So what we need to perform is this integral and this integral. And but that's super easy because we just do a d-dimensional integral instead. So that can be just performed by just using moving from the Euclidean coordinate, the Cartesian coordinate to the spherical coordinate in d dimension. That is super easy to do with omega d. And then r is super r, and then r squared r. Like this. So this is radial dependence, and this is the angular dependence in the Euclidean range. And that will give you, this one will give you the volume of the volume of sphere, d-dimensional sphere, and this one you can manipulate into. And then the x. So this is just a change of variable. One can do that. 1 minus x b over 2. Or change of variable here is the x is equal to down r squared on down. That's the change of variable. We can do the same thing for, oh my goodness, I didn't write down the integral star. What you should tell me if I do something wrong. And now next to the same thing, you gotta make a mistake, just point me out. Anyway, even lecture note, if I find a typo, just tell me some students time to do that for me. It's a very similar computation, and then 2 times alpha 2 minus b over 2, and then the omega 2 x 1 minus b over 2, and then this kind of integral already appear in, I think, huh? 18th century by Euler. So this kind of integral here. This one and this one is Euler or Bernoulli and so on. It appeared, and then the alpha beta is equal to I mean this kind of integral was studied by Euler from Euler, the time of Euler, and it can be written again function. Euler, Bernoulli, Jacobi, and so on. People study like this way, and then the volume of sphere can be written as 3 pi. D over 2. This is, and also it can be also written gamma function like this. Okay, so that's the continuation here. Okay. So therefore, if you plug that into here, let me continue here. That's better, to be honest. Okay. I mean, it's just this one. The result this one is just applied to here, so it's super simple. So now here is the alpha is equal to minus d over 2, and beta is equal to 3 over 2. No, 3d over 2, and just use this one. Correct. D over 2, 3d over 2. Yeah, I think it's uncorrect. So you know, see this one, right? Gamma n is equal to is it correct? Is it n minus 1? Which one is correct? N minus 1. Thank you very much. N minus 1. So you have to use this relation. If n is if n is natural number or then gamma n is n minus 1 factorial. Is it okay? So then you have to use this problem. Okay. So then if you use this property, continue. So one can show up the following, so gamma 2 is nu of q squared is equal to minus 4e squared, and the overall factor is a factor of 4 pi over 2, 0 down dx. and then the piece. Kind of annoying to repeat again. Minus G, and then 1 minus x cubed squared plus m. Okay. And now we just noticed that the dot I unfortunately slightly left here. Okay. 1 minus x cubed squared minus m squared. So this term is coming from the first line. The first line here. And this term is coming from, is giving this bracket. This bracket. Maybe I should write down. This term coming from first line. And this term is coming from second line. First line over there. Or even first line here or second line, whichever I call it. And then the plug this body of delta into here. And we just notice that the yeah. So this plus m squared, and but there's a minus sign here. Okay. So plus m squared minus sign here, and minus m squared times minus gives a plus m squared. Then m squared cancels. And what's left is x times 1 minus x, and the x times 1 minus x. And here also you have x minus 1 minus x magically. It's very beautiful. So therefore you can factor out. And what's left is that the desired form of things. I hope I can open any mistake. Alright, let me check my computation. This is strange. Yeah, I think it should be okay. Okay, so d over 2, d over 1, dx, and then what we have is 2x, 1 minus x divided by delta 2 minus d over 2, and then times beautifully this term will show up. Now q squared times g mu nu are short from here. Q squared times g mu nu, and if you add them up, you get 2 times overall factor 2x, 1 minus x will show up, and then you have a q nu. The helpful, so this is exactly what the word identity would tell us. So pi 2 mu nu is also an order alpha to give you proportion. It's a very beautiful. Helpful. This means that the this part is equal to pi 2 cubed. Unfortunately, yes, I think this is yes, pi 2 cubed. And then now we notice that the so this term will give you divergence first. So what's nice about dimensional regulation is that they put all the infinity into this down function. So what we are going to use is that the maybe I should use this. When v equals to 4, gamma u minus d over 2 is equal to gamma and gamma gamma 0 has a pole. Gamma, so the epsilon, so we think about the epsilon is very small now, and then when epsilon is very small, this has the divergence something like this one is equal to E/2 minus gamma plus order epsilon, and this gamma, I mean, in quantum physics, there are lots of gamma out here. Since gamma is not the gamma matrix, not the photon, not the indices, it's called Euler-Marchevani constant. This is called Euler Marchevani constant, where the gamma is approximately equal to 0.5 something. Yeah, 0.5772. So now infinity really appears when you take b equals to 4 minus epsilon. So this is the prescription of this dimensional relation, and the infinity will show up here. And this is the similar kind of the Oh, sorry. Thank you very much. Sorry. 2 over epsilon. Sorry. Thank you very much. 2 over epsilon. Thank you. Yeah. So this will give you the infinity. This is a similar kind of this is infinity of the dimensional regulation. This is log lambda square, log divergence in power zero. So this is the close kind of the log divergence in power zero. Okay. That's what happened. Unfortunately, 10 minutes left. Okay, so now we apply the same thing in the Q squared is equal to minus 4 epsilon squared. I mean, it's just our function, and this gamma will give you this divergence, and then 0, 1, the x to x 1 minus x. And here you have to be careful. So here, so this part, I should use a different color. This part is indeed equal to 2 minus the epsilon over 2. Okay? Delta to the epsilon over 2 can treat it as the 1 over delta epsilon over 2 is something like that. How do we treat this one? It's minus so 1 minus by Taylor expansion 1 minus the epsilon over 2 log delta plus order epsilon squared. So you can just do the Taylor expansion of this one, and then you get this one. How can I justify it? I think it's just an ordinary Taylor expansion. What's the right way to do that? How do you see this is the right way to do that? Unfortunately, I don't have a time to explain. Let me explain it away. So therefore, this can be replaced. I'll call it a 1 minus epsilon over 2 log of delta plus order epsilon squared. So sorry, I think it's better to take a log of it. Minus epsilon over 2 log delta. If you take a log of this one, and then if you take right hand side and take the epsilon. Sorry, I just got confused. So I think this should be easily something like this one, right? And then, yeah, okay, so, sorry. So it's correct. 1 over delta epsilon over 2 is this one. And this is a cell expansion like this way. Log of delta plus order epsilon squared. Okay, do you understand? Is it okay? Okay. And this one, and if you manipulate this one, this can be written as minus 2 alpha over pi, 0, 1 x, 1 minus x, 2 over epsilon minus log of m squared minus x minus 1 minus x, q squared minus gamma plus order. Okay, and what we are interested in again, so here's the infinity up here, but we need to take the distance always. But we are interested in difference from 0 to q squared. That's what the calculator told you. So what we need to do is to take difference of delta to q squared, pi to 0. And if you take a difference, you just set the q squared to the 0 and take a difference, then unknown infinity disappears, and then what we have is 2 alpha over pi over 0, 1 dx x 1 minus x log n squared and square minus x 1 minus x q squared plus order squared. Fine. And then if you take the high energy, so if you take the limit q squared minus is a bit higher than the mass of the electrons, then what we have is alpha over 2 pi log of minus q squared and 5 over 2. Okay, so that's the result. Therefore, what we have at the order of the, when Q squared is very big, this term is dominant. And you just log x minus 1 minus x and then x times 1 minus x. And do the integral, what you get is this numerical factor, and this therefore, so it's just alpha over one minus. Okay, dependence of the structural constant is really like this way. Now of course, alpha and alpha effective is just that when this term is equal to 0. Okay. So of course, I tune this one in such a way that the distance is equal to 0 at alpha effective minus q squared is equal to alpha. So you can, if you solve this equation, you can see that what is the value of q squared. Okay. If you solve this equation is equal to 0 means essentially okay, when okay, so log minus q squared minus m squared is equal to 5/3, which means that what's that answer? This means that the minus q squared minus m squared is equal to e to the 5/3. Therefore, this means that the minus q squared is equal to m squared times e to the 5/3. When energy is just roughly m squared times e to the 5/3 alpha effective. We tuned alpha effective. So let's call this value is equal to energy E0 is equal to alpha. Is equal to alpha, and this is essentially about 1/137. And as I mentioned, okay, time is over. You start with E0 is around here. This is E minus q squared, and alpha constant, alpha effective. Then you start with 1,137, and if you go to high energy, it's the log divergence that will show up here. Okay. Let's come on top and fine. Any question at this moment? Okay, so therefore, for this one-loop analysis, we tell you that the coupling constant grows as the energy grows, and it really depends on the energy you measure. So this is purely quantum mechanical phenomenon. After the analysis of the one-loop diagram, and then next week I will show this is equal to this vortex energy, and this is the really beautiful result in quantum QFT1. So I think yeah, you can look forward. I think yeah, this is one of the most beautiful results in the quantum QFT1. Yeah. So let's stop here, and then yeah, if you have a question, I will talk